So we're thinking about this as two parts. The first part for the plane at 525 miles per hour and 125 bearing. I'm going to start by kind of drawing a picture. So when I draw the bearing, we're going to start from north, and we're going to go clockwise 125 degrees. So here's 90, and then like 35 more. Gets me to 125 degrees. But to actually do any calculation, I don't want to use the bearing angle. I want this standard form angle. So I'm going to call that angle theta 1. So that angle would be 90 plus 90 plus 90 plus the complement of 35, which would be 55. When I add those up, I get 90 plus 90 plus 90 is 270, and then 55 more is 325. So now I can break that journey down into a horizontal component and a vertical component. The horizontal component is 525 times cosine of 325, and the vertical component is 525 cosine of 325. I can break the wind down similarly. So just like I did for the plane, I'm going to draw the wind. So we have a 200 degree bearing. So we're 90, 90 is 180, and then like 20 more gets me to 200. But again, I'm not interested in that bearing angle. I want my standard position angle. So that would be a 90, 90, and then the complement of 20, which is 70. So 90 plus 90 plus 70 is 250. So then I can say I have the horizontal component for the wind is 35 cosine of 250, and the vertical component is 35 sine 250. So my final position then, I can find by just adding up the horizontal and vertical components. And for that, I'm going to use the calculator. So the first thing I'll do with my calculator is I'll check to make sure that I'm in the correct mode. What mode should I be in for this problem? Degree mode, because my angles are represented in degrees. So for the x's, I'll do 525 cosine of 325 plus 35 cosine of 250. Which gives me 418.01. And then I'll do the same thing for the y's. So 525 sine of 325 plus 35 sine of 250. So that's going to be 418.08. comma, negative 334.02. Everybody okay with that so far? So the next thing I'm going to do is I'm going to draw that final location. So if I go 418 over and then 334 down, I would be somewhere down here in the fourth quadrant. And if we want the bearing, what we're looking for is this angle. In order to find that, though, I know it's going to be 90 plus something. To figure out what that something is, I'm going to use my standard position angle to kind of figure that something part out. So I'm going to call that standard position angle here theta f, because this is the final position. So to calculate that, I can use tangent inverse of the final y over the final x. And to do that, I'll type that into my calculator. That comes out to be negative 38.62, which is describing this angle, which is great news for us, because what does that tell us that something part is? Just 38.62. Why did we get to ignore the negative? Because bearings are only positive angles, so it doesn't matter which direction we're going. Bearing, we only consider going in that clockwise direction. So the positive or negative doesn't really matter to us when I'm converting that angle into a bearing, or to something I can use to keep part of a bearing. So I can say my final bearing then is going to be 90 plus that 38.62. And then we still have one last thing to do, is we need that speed. To do that, we can use the Pythagorean Theorem. So we'll just take the square root of the final x squared plus the final y squared. And just worth noting here, I'm including this set of parentheses around the final y, because the sign on that final y is negative. If I don't put the parenthesis around it, the calculator is going to goof that up on me, because it'll square first and then make negative rather than making negative and then squaring. Anyways, that gives me then my final speed is 535.13. Does everybody feel okay about that? Hopefully a little better than when we saw these the first time. What would you do if there were, say, 3 things going on? Would anything really change? No, you'd just be adding up x1, x2, x3, y1, y2, y3, right? If I had 3 things that were kind of affecting what was going on. Okay. This problem here is a little bit different, though. Let's read this situation. It says a plane can travel at 480 miles per hour under its own power. The pilot sets a bearing of 320 degrees. As the plane travels, the pilot notes that the plane is actually traveling is at a bearing of 325 degrees and a speed of 472 miles per hour. And we're asked, what is this bearing and direction? It's still the same question. Or what is the speed and bearing of the wind? So what we observed from the last problem was we saw that when we added the plane and the wind together, we got that final result, right? Like how fast and what direction the plane is actually traveling. Here we're asked about the wind. So how would we be able to get the wind by itself? We'll just do final minus plane. Just like basic algebra kind of stuff, right? Okay. So what we can say then, it's going to be xf minus xp, yf minus yp, where I'm using f for the final and p for the plane. I'll use w for the wind as my subscripts. You're welcome. Everybody okay with this idea so far? So, what part of this information is the final? That information is our actual result. That's what the plane is actually doing after it's taken off and encountered some wind, right? So let's turn that into components. So 325 degree bearing. So we have 90, 90, 90 is 270, and then 55 more. Gets us to 325. But we're not interested in that bearing. We're interested in the standard position angle. So 90, and then the complement of 55 is 35. So I'm going to write this as theta f as 125 degrees. So my xf is going to be 472 cosine of 125, and yf as 472 sine 125. And now I'll do the same thing for the plane. So the plane is a bearing of 320 degrees at 480 miles an hour. So 320, so that's 90, 90, 90 is 270, and then 50 more puts us over here. And again, we're not so much interested in that bearing as we are in the standard position angle, which I'll call theta p. So that's going to be 90 plus the complement of 50. So that's 130 degrees. So xf then is going to be 480 cosine of 130. And then, oops, I don't mean f's here. What letter do I mean as my subscript? P's, right, for plane. And then 480 sine 130. Everybody feel okay to this point? So up until this point, nothing is really different. This is the only place where it's going to be different. So the wind, to get the xy, or the xw and the yw, I'm going to take xf minus xp, and then yf minus yp. This is the only place that it's different than the previous problem, right? Is that here we're subtracting the components rather than adding them. So we'll do 472 cosine 125 minus 480 cosine of 130. And then 472 sine 125 minus 480 sine 130. So that's going to give me 37.81, comma 18.94. And now, just like before, I'm going to calculate the bearing the same way. I'll start by plotting that point. So 37 over and 18 up puts me somewhere in that first quadrant. And my bearing is always drawn from the north back to that clockwise to the terminal side. But I'm not interested so much in that bearing. That is not going to be directly calculable for us. Instead, what will be directly calculable is that standard position angle, theta W, W for wind, which is, I can calculate by doing tan inverse of y over x. And when I type that into my calculator, I get divided by 2. And I get 26.61. So my bearing then is just going to be the complement to that. Which when I subtract 90 from it, I get 63.39. Everybody okay there? And then for the speed for the wind, I can calculate this again just using the Pythagorean Theorem. So I can take xw squared plus yw squared and then square root it. And there I get 42.29 miles per hour.